Okay, cool. All right, good afternoon, everybody. Let's get started. I'm Saraj Manjal. I'm also okay with pronouncing it as Siraj. And today I'm going to talk about DDL schema migrations at scale. This topic has been a deep pain point for us over at Robinhood over the years, and I'm going to tell you all about it today. But first, a little bit about me. So I'm a senior software engineer at Robinhood. I worked in the storage infrastructure domain for more than 5 years across Google and Robinhood. And the past 3 years at Robinhood have been focused on Postgres. In the distant past, I also did some Android and backend programming. So outside of work, I live right here in Kirkland, Washington. I love hiking and the outdoors, which is kind of a par for the course thing in this area. And there's a few of my favorite hikes, the Chain Lake Sloop at Mount Baker, and then the Enchantments Trail and Stairway to Heaven in Hawaii, which are like really nice. If any of you are visiting from outside of Seattle, I recommend like go hike if you can on one of the days. It's beautiful. Oh, and I'm also a huge Arsenal FC fan. That's a soccer team in London, and it's like really close to my heart, so I'm putting it on here. Okay, let's get started. What exactly is DDL, and why are we talking about it today? So DDL stands for Data Definition Language. DDL happens whenever we need to modify our database schema. So this can be creating or dropping tables, adding or deleting or modifying your columns or indexes or constraints, and similar things. But why does DDL happen? It happens all the time because new features have to launch, product requirements can change, and sometimes humans just pick the incorrect schema to start with when they're building products. Let's talk about why DDL is hard to run. A lot of DDL statements will acquire heavy locks, which can block other queries. Some statements will also do table scans, which is when they have to visit every row in Postgres tables. This makes them run for a very long time while they hold on to those expensive locks. At scale, which means high traffic to these tables and table sizes being very large, there are two main problem areas. The first one is long-running DDL statements due to locks and table scans. And there's a second area called backwards compatibility, where many application versions will talk to the same database in a distributed environment. Let's dive deeper into long-running DDL statements. Most DDL statements will acquire access-exclusive locks. These are the most expensive locks in Postgres. They will block all reads and writes on the table. Luckily, some of these statements are super quick and are metadata-only changes in Postgres. The database doesn't have to go and visit every row. Examples are alter table, add or drop column. These will finish in like milliseconds. But some statements, like adding a unique or not null constraint, can do table scans and hold the exclusive lock for very long. And here's a fun fact. Before Postgres 11, alter table, add column was also a table scan. And this is a battle scar that we have at Robinhood. But not all DDL takes locks that are this expensive. Some takes more lenient locks. So create index will take a share lock, but it still has to scan all the rows because it has to build the index. Adding a foreign key constraint takes a slightly different lock called share row exclusive lock, but it also needs to visit all the rows and validate the foreign key constraint. These locks are slightly less expensive. They will block only inserts and updates and not any reads to the table. Okay, here is a short demo that I prepared. Okay, so we have this table called product, which has 4 fields: ID, name, description, and quantity. And right now, I'm running a select count star from product to tell you how many rows it has. It's a pretty big table. It has 10 million rows. And now we're going to try adding a column to the product table. So we open up a new transaction, and we write our SQL, which is alter table add column image ID. So imagine that you're adding an image ID column to your table. The result's going to be the same even if you have a not null here. But yeah, it takes 1 millisecond, which is super quick. It held an expensive lock, but it was super quick. I couldn't even literally have showed you the lock was held because it finishes so fast. But now let's try adding an index on the description field. And product descriptions are pretty gnarly, so the index is going to take a while. I open up another transaction on the second shell. I select a couple of rows. It's a read only, and it still works. The index doesn't block it. But when I'm trying to do a write by inserting, it gets blocked. And that's it. That's the demo. Cool. This kind of happens. So, okay, we are back here. And yeah, sweet. So we just saw queries being logged with logs. And this can lead to big trouble. Imagine this. Your table has millions of rows, and the scan is going to take minutes or hours if the number of rows is in the billions. If this table is seeing high traffic, a high number of queries, we will see long queues of blocked queries because the head of line blocker, the create index, is never finishing. At this time, because all the queries are in an active state waiting for the index to finish, the host CPU is going to hit 100% usage because of constant cycling. At this point, it doesn't have any bandwidth to respond to a new connection being initiated. And because none of the queries are finishing, if you have a proxy, a connection pooler, it's going to hold open all the connections. So with time, even the connection pooler is going to get backed up. And because the host is at 100% CPU, it can't even get a new connection. So everything is maxed out. And at this point, you have a service outage because nothing can talk to the database. All of this because you were trying to create an index on a table which runs hot. And this has happened to us a few times. So how do we get around this situation? Our solution is to kill this long-running DDL, but with kindness. We have a runtime strategy. We have some tooling to run the DDL with, and here's what we do. We pin a connection for the DDL on the connection pooler. So we want to lock it down to a specific session, and here is why. We're going to add session-level timeouts. So lock timeout will enforce that each statement quits early if it is waiting on another lock. And statement timeout is like a catch-all. It'll make sure that whatever workload you're running, if it's doing a long table scan or something, it just quits early. In this case, your damage only gets limited to the duration of the timeout, so you're not blocking anything else for more than 10 seconds. And we also add defense in depth here by acquiring a manual share update exclusive lock. This is a lower level lock, which is supposed to run nicely with other reads and writes, but it's a watermark. If our tooling cannot acquire this lock on the table, that means the table is running very hot. And if we run DDL on it, it's going to cause a lot of damage. So these are like the three defenses we have at runtime. Another interesting thing here is that we run DDL in transactions, which is, in my opinion, a really cool feature of Postgres. So if you encountered a failure because of the lock timeout or the statement timeout, you are free to retry later. And in our case, we retry our entire application deployment, which runs the DDL along with it. And we do this at a time when there's lower traffic. Like if you got a lock timeout, it means you were running hot. So you have to retry later. So here's our general architecture for database interactions. We run on Kubernetes, so we have an application container, which talks to a sidecar PG bouncer. This is all in the same pod. And then we talk to a global PG bouncer. This is like a shared global connection pooling tier, and that talks to the Postgres database. If you notice here, we run the global PG bouncer in transaction pooling mode with pool sizes typically in the hundreds. This is the recommended practice to run with high throughput. If you have transaction pooling on, it cycles connections quicker. But for the DDL solution we talked about, we need to pin a connection at session level so that you can apply all the timeouts. That's not possible with transaction pooling. So we added a small PG bouncer tier just for running DDL and made all the DDL traffic talk to that. That PG bouncer runs in session pooling mode. If any of you use RDS proxy, there's other ways to achieve pinning, but PG bouncer doesn't support this, so you have to rely on session pooling. But catching things in production is kind of too late. You don't want to find out that things are going to time out in production. So we also have a pre-runtime strategy. We want to detect all these table scan scenarios early on in our pipelines. So we add warning linters for DDL generated by all our microservices. We also have mandatory code reviews for our critical customers, in the sense like the critical microservices. And we cannot solve for time taken on large tables. So anytime you have these DDL operations, it's going to take time. Can't work around that. The workaround there is just partition them. But with what we have, the best we can do is try to reduce the lock levels. And here are some practices for doing that. So if you're going to create a foreign key constraint or a check constraint, you can do that by adding the not valid clause. So the part where I talked about earlier, every record being validated for the constraint, that gets skipped when you're applying DDL. But you have to validate it at some point. So you just do that later, out of band. If you run the validate command later, it acquires lower level locks. So we basically split the problem. Similarly, we create indexes on large tables out of band with the concurrently keyword. This, yeah, go ahead.
What does out of band mean?
Out of band means, and this is something that will become a little clearer a little later, which is we run DDL with our application deployments. Yeah, so when we're deploying a new application version, if it expects a schema change, that schema change is going to go out with it.
Okay.
Yeah, so I don't want to block everything. Yes, so yeah, so out of band here means do it outside of the critical DDL time window. Sorry, go ahead.
Or does it create index concurrently? Is there a way for your migration script to still
Exactly, so we do this outside of the migration script. There's another pipeline to do it. Because, yeah, if it's a large table, it's going to take as many, it's not going to take big locks. It's not going to block other things, but it's still going to take time. So you kind of have to do it when you're not blocking other things, and preferably at a time when there's low amount of traffic to the table. Great questions. And similar to this, if you want to add a unique or primary key constraint, you do that by adding an index with concurrently out of band, and then your DDL for the primary or unique constraint becomes really short. You just do add constraint using an index. So the results of all this work have been pretty good. Our runtime checks are effective at catching contention and timing out, thereby preventing incidents and limiting them to a few seconds. And runaway DDL statements sometimes still happen because our ORMs will do unexpected things with DDL. I think that's a common theme with ORMs. But on occasion, we find really interesting stuff. So this one time, we were changing the size of a varchar column. It's typically a very safe operation. You do not need to scan the table or rewrite stuff. It's supposed to be instant. But in this case, we had a table scan, and we dug deep into the Postgres code. We found out that it's a super edge case. So if your column has a conditional index using the any operator, it's going to rewrite the index if you try to increase the size of the data type. So like some gotchas are still there in the wild. But this is still a massive improvement over the past, and we have very few incidents related to this problem area now. I can pause here for any questions around this topic. Yeah?
So you mentioned concurrent index creation.
Yeah.
When you're trying to dial in the duration for the timeout for your statements,
Yeah.
how do you gauge how much time to add? You know, like if I say give it a minute and it times out, how would you go about dialing in? Like, oh, I should give it 2 minutes or 5 minutes or an hour.
Yep.
How do you handle that?
That's a really good question, and there's nuance to it. So we have load testing environments, and where we have similar data size to production, not the exact same data, not the exact amount of data, but it gives you a fair idea. So if we are not sure, then we're just going to do a quick load test and see how long the DDL takes there. But typically, we stick to 10 seconds because there's many ways in which there can be locking, and we want to restrict the impact. So even if, let's say, you have a table with maybe 1 million rows, maybe it finishes a regular create index without concurrently in 20 seconds. We don't want to risk it. We would rather like first catch it pre-production and change the DDL, run it out of band. Or if it still makes it to production, we would want to kill it early on. So like we typically stick to 10 seconds only in like a very few cases when we are sure that it's a concurrently, like you asked, it's safe to run it. We'll increase the timeout a little bit. Yeah. Yeah.
On the same lines, so if table grows, then you check the log time of the load testing environment, and then make the adjustment in production.
So yes, but we typically never do this. It's just like a super exception case. Like we have other pipelines to run like index concurrently outside of like the regular deployment flow. Yeah.
Can you just elaborate on the ORMs do complicated things?
Yeah. So I'll tell you a story about a fun incident. We use Django a lot at Robinhood, and somebody added a new column, and they also wanted an index on the column. So Django did a very simple thing where the SQL was begin, add column, add index, commit. So the table was very large, but maximum, like even if we ran this SQL directly without any protections, it should have only, like if you're creating an index, it should only take the share lock, and it should only block writes. But we saw reads were also blocked, and everything was blocked. And the reason was it did 2 operations in the same transaction. Like if you added a column and closed the transaction, then that higher lock level would have only lasted for a very small time. because you were combining the two operations, you had a higher lock level.
Okay, then both the lock kind of escalated.
Yes, exactly. So
Lock escalation happened.
yes, yes. So it's very easy for like ORMs to do this stuff, and sometimes you get bit by that. So you have to be defensive. Yeah.
So only way what would you done was taken the DDL out of the ORM, do it normally through the.
Yes, yes, yeah, through other pipelines. Or like, but like the splitting point still holds here. Like if the ORM can be extremely granular with its transactions, then that helps. Yeah. Cool. All right, let's move on to the second problem area, backwards incompatible DDL. This is super common if you use ORM systems because they typically have DDL migrations tied to code. Examples of this are Django, Ruby on Rails. And at any point, the application model, or which can be like Java classes or Python objects, they expect the database schema to be in a particular state. So I'm going to walk us through a deployment of some DDL alongside new code and see how this can break our system. We have this product table on the database over here, down here, as 3 columns. And then we have this old application version running, which has ID, name, description. Like the schema is totally in sync with the database state. So it's all good. We'll see that all read and write queries are working from this application version. And at this point, we start a new deployment, which is trying to run a DDL. And the DDL is alter table, add column, not null. And note that it is not providing any SQL level default. Everything's good at this point. The old version still has all reads and writes working. And we just saw in our demo that this operation is pretty short. It's going to finish in milliseconds. It takes expensive locks, but it's pretty quick. And so the new version's compute comes up after it has applied the DDL. The new version's model state has an image ID field, which matches with the new database state, the image ID not null column. So reads and writes are working fine from the new version. But at this point, what we'll notice is that writes from the old version are failing. Why does this happen? When Postgres gets a write from the old application version, it doesn't get any value for the image ID field because the old app model doesn't know about it. So you get this error because the column is not null, so Postgres just rejects it. And at this point, all the writes from your old app version are failing. This is a classic backwards incompatibility example. So if your service has low traffic, you're only getting a few requests per second, this doesn't really matter. You can just eat a few errors from the old app version and wait until the new version fully deploys, and you're done. But if your service is really critical, or you have very sensitive error thresholds, like if you're dealing with financial data, you have a big problem. Many systems, while deploying stuff, will use health checks, and health checks often rely on error rates. So if a health check notices that error rates on the old version went up as soon as you deployed new stuff, it's going to roll back to the old state. If you roll back to the old state, all your writes are failing, 100%. So again, service outage. And now a question comes to mind. Why can't you just roll back the DDL change you did? Because the previous database state was working completely fine with the previous application version. Why can't you roll back both of them? You can't roll back because you made an additive change. You added a column, and it got some writes from the new version, and there's customer data in there. So again, you're at a full service outage. What do you do? So one way is to, again, catch this before it gets to production. The nature of the problem here is nuanced. Like, you can't detect it in production because you have two versions of your code running. And if you write unit tests for each version such that they talk to a database embedded in your code or with Postgres, like a Docker container, each version is going to pass its own unit tests. And linters or static validation are also not very effective because there's not enough information about the old and the new app version. So we brainstormed a little, and we were like, okay, so we want the old application state to be tested exhaustively against the new database state. How do we achieve that? We packaged all of our tests into Docker containers and pushed them up to remote repositories. So anytime somebody will make a new schema change, you would pull down the Docker container for the version currently deployed in production, which is the old version, and has all its old logic. And you would test that with a Postgres container containing the newer DDL change. So you're testing the scenario that we had in production, like how old code behaves with newer database schema. This was effective. We could reproduce all the errors that we were seeing. But the means to get there was pretty tough. So packaging a lot of stuff into Docker containers and maintaining it was a tough problem. It wasn't scaling to hundreds of microservices. I am a storage engineer, and I was working on implementing a test toolchain in the end. So we thought, okay, we have to simplify this and break it down. So we decided to not run all the tests and focus on the 2 bits of information that we really need. For every version, we need the model state and what schema state it expects. So essentially capture the database and model state at each app commit. So we built something called schema state. And the pipeline here looks like this. So anytime you have a new schema change, you're going to build a new schema state. You're going to test it against the last known good version in a transition test. And this has a bunch of rules. If you pass the rules, then your DDL is safe to deploy, and it would not cause a backwards compatibility issue. And if that happens, we also update the last known good state. But if it's not safe to deploy, we catch it before it goes to production, and we use workarounds. So here's what schema state looks like. It's essentially a giant JSON where we capture information about every table and every column in the table. So for our product table and the ID column, we're capturing what its state looks like in the application model and what the application model wants the database state to be. And the information is the application type, like a string in Python or Golang. If the column is nullable according to the model, if the model is encoding a default value, and if it's ignored by the model. Oops, sorry. And also similar state on the database. Like this is the database type, nullability on the database, if there's a default value on the database, and enum values for custom types. And in the example that we walked through earlier, this test will have an old schema for the old version of the application. And a new schema state that's built will be tested and it'll get a missing default value error. Because if we had a default value on the DDL that we executed, then we wouldn't have got the write errors that we did. So that's how we enforced backwards compatibility. Here are more scenarios apart from the default scenario. If you're dropping any columns, it's backwards incompatible. The old version can't deal with it. It's going to fail all its read and write queries. But it is possible to do it if your older application version is ignoring that column. If you remove the column from your object, imagine that. So in that case, it's going to work. Similar story with renaming and altering types. So if you rename, then the old version is going to break again. And the workaround is to drop the column safely and add it back with the correct name. Oops. And if you're doing a type change, the solution is to add the column with the correct type, do a backfill, and then drop it safely by ignoring it. So we built this whole simpler test suite. We deployed it across all of our microservices. And the results have been pretty good. So we've had almost 0 issues with backwards compatibility. It's been pretty effective. And we're going to invest in more framework support because what we built has integrations with our ORMs. We kind of talk to the ORM layer to get information about the model state. And we only support Golang with SQL C and Django, which are our 2 main languages and frameworks. With time, I'm sure we'll discover more rules with backwards incompatibility scenarios, and we'll keep adding to the framework. So there's some common questions that people have about this whole approach to backwards compatibility. I'm going to get ahead of them and try to answer them up front. So why can we not stop traffic to apply DDL, like take a maintenance window? Because we live in an always online world. People use applications all the time. It's not always possible. And we have trading systems which are always active. It's not possible to stop traffic. Why couple DDL with app deployment? So this is how a lot of ORMs are designed. Like if you're making a change in the model, it expects it to be on the database. So DDL first is how a lot of stuff is designed. And there's an argument for doing it manually always and not tying it to the application deployment. But that doesn't scale to hundreds of microservices. We would just be applying DDL all the time. So manual is not an option. And why stick to DDL before code deployments? So there's a new trend with some frameworks recently. PG role from Zeta is a good example, where they split DDL into 2 parts, a pre and post DDL. If you do that, and also they use indirection with views. If you do that, then this problem is still there, but it becomes a lot less damaging. And why we can't do that is because they have their own kind of language for writing DDL. It doesn't integrate with any of our ORMs. It's a lot of work to move to that solution. PG role. Yeah. So yeah, things like this do exist, but for us it was simpler to write this framework and roll it out everywhere, which plays nicely with our ORMs, and we don't need to modify any code. So yeah, thank you so much. This is it, and I'm open to take questions now. If you have any feedback or questions, you can also reach out to me through social on my website. Yeah, thank you so much. Okay. Yeah, if there's any questions. Thank you.